So in our next section, we're going to begin our discussion of interior gateway protocol routing, or IGP routing, in JunOS, both for IPv4 and for IPv6 address families. We'll talk a little bit about the router IDs in JunOS. As I mentioned before, there's a difference as to where you set these as compared to iOS. This is going to be once global for the entire system. We'll also talk about routing policies and then how these are used to implement filters both inbound and outbound. And then we'll see some more advanced examples of this later when we're using the routing policies for BGP policy application in order to modify the BGP best path selection. Then we'll talk about RIP routing in IPv4 with RIP version 2. We'll talk about RIP routing in IPv6 with RIP-NG. Then likewise OSPF v2 and OSPF v3 for IPv4 and IPv6 respectively. And then finally ISIS routing both for IPv4 and for IPv6. Now, as we had previously talked about in terms of the router ID, this is one of the minor differences between the OSs, but it is important to note that the router ID is going to be global to the JunOS process. This means that when you configure it once globally, this is going to affect OSPF and BGP and things like LDP, for example, where in the case of iOS, typically you would have to set that on a per protocol basis. So in general, this is going to be always one of the first options that we want to set before we configure routing, because if we have any type of, let's say like a virtual link in OSPF or any type of authentication and LDP that's based on the router ID as the transport address, we want to make sure that that is not changing its operation if the box reloads or an interface goes up or down. So in the case of JunOS, that is applied globally under routing-options, and that's where we saw previously where we would configure options like static routing. So from the CLI, if we go to configuration mode and we're going to edit our routing-options, and if we say set question mark, this is where we would configure the router ID, but also we can see that there's a bunch of other generic routing options that we would also set under this mode. So if we had our topologies, which we saw previously, that was talking about our virtual routing and forwarding instances, or if we have things like VPLS or L2VPN, we can also say like what are the invalid routes that we would want to filter out from globally from all of the protocols. This would be things like the RFC 1918, for example. Maybe if you're not using private addressing, you can use this to have the router discard those routes. And then in this case, we have the router identifier, which is going to be a global option. So just like in iOS, this applies to not only IPv4, but also IPv6, because protocols like OSPF v3 and multi-protocol BGP for IPv6 routing, even though they're using IPv6 as the address families that they're advertising, they still use a 32-bit address as a router identifier. So like I mentioned, just in general, you would want to set this particular option. And normally, if we look at the run show interfaces terse, you would normally set this to be equal to whatever your loopback interface is. So assuming here, like the loopback is 9999, we would say set the router ID to be 9999. Commit and quit. So then we're going to make sure that once we start any of the IGP processes, that this value is never going to change again. It also makes it easier for us to verify the state of the network. Things if we're looking at like the OSPF database and we look at an advertising router, or we're trying to decode a link state advertisement, we want to know who is the originator of that, and the originator is going to be based on the router identifier. Now the next step that we have before we start the IGP process, and first we're going to look at RIP version 2 here, the next step we need to do is to define a routing policy. Now, a routing policy is going to be similar to a route map in iOS or the routing policy language, the RPL, in iOS XR. Now, we'll see that from a syntax point of view, the routing policies in JunOS are more similar to iOS XR because they have very granular matches that you can do. There's all sorts of hierarchy and inheritance that you can do, and there's a lot of branching logic that you can use through the statements. Where in the case of regular iOS route maps, it's normally just a top-down process that we say if the match is true, then we're going to perform some action, like permit or deny a prefix, modify options like maybe a tag value if we're doing redistribution, or modify attributes like local preference, AS path information if we're talking about BGP. So in the case of JunOS, all of that is going to be applied here under the routing policies. So not only is it going to be used for filtering in terms of both inbound and outbound prefixes, it's also going to be used for attribute manipulation. So mainly we'll see that's going to be used for the BGP best path selection modification. Now, the routing policy specifically is going to be defined in configuration mode under policy options. And we'll see this is where we would configure any of our filters or like an AS path list that we're going to use as our criteria for creating the actual policy. So if we look at in the CLI, let's go back to top and let's edit our policy-options. And we edit question mark. We can see under here that we can create prefix lists. So prefix lists similar to in iOS or iOS XR. This is how we would match against a route in the table, either for IPv4 or IPv6. I could say match all of my loopbacks that are /32, and then I want to permit or deny them from being advertised. So it's the same type of logic for matching against both the addresses and the prefix length that we have in both regular iOS and XR. We then have our AS path information. We have communities, both standard and extended communities. We'll see this would be useful generally with global unicast BGP routing. Like if I want to apply a traffic engineering policy based on the community values that my customers are signaling, typically based on RFC 1998, which is the same way that regular iOS or XR implements this. So I signal you a community value, and then based on that, you take that and you set attributes. You set local preference, you set the communities like no export, no advertise, and we're going to be basing those. We'll see when we get to BGP, based on accepting particular community values, we can then take actions with the routing policy in order to modify different attributes. So in our case here, we're going to be creating a policy statement. So we're going to edit the policy statement, and we're going to configure the policy name. So this is essentially the equivalent of the route map name or the RPL name in the case of iOS or iOS XR, respectively. So like any of the other statements in JunOS, just like in iOS, this is going to be case sensitive. So we'll say, for example, we have policy 1. Now, under the policy statement, if we say edit, this is where we're going to determine the logic of essentially if-then-else statements, where specifically they're using from, but from a logical branching structure point of view, the keyword from really means if-then, or I should say it means if. So in this particular example, we have a policy that says the term is 10, which 10 is technically not a number here, it's just an arbitrary string, where it's saying if the protocol is OSPF, then the action we're going to take is to drop the particular update or the whatever we're doing with routing. So for example, if we were using this for redistribution, which is what we call exporting in the case of JunOS, we could say when I export to BGP and the route came from OSPF to begin with, then it's going to be denied. Now we'll see with the RIP implementation, this is required to configure a routing policy before we can advertise any routes to the particular neighbors. So we'll see one of the most basic policies here would be similar to in iOS XR, where in XR we would do something like this, where we would say in global config, our route policy permit is going to say, well, technically it would probably call this pass. Route policy pass that just says pass end policy commit. And then in the case of XR, if we look at the show RPL, for our routing policy language, this says that there's no match criteria. Whatever we're using this for is going to be an explicit permit. So then if we were to apply this outbound or inbound to eBGP sessions, it essentially means that you're going to allow all updates inbound and outbound. Or likewise, if we were using this for redistribution, that would basically say permit all updates back and forth. Where normally in the case of iOS, you don't explicitly need to set a route map. Normally you would for policy control in terms of like BGP inbound, outbound updates or redistribution, but it's not 100% a requirement. In the case of JunOS, it's more like iOS XR, where a lot of times the RPL is required in XR, Like in our case here, we'll see that the routing policy is going to be required for applications like RIP routing, for example. So back to the JunOS CLI, we're going to say edit from. Actually, we're going to edit a term. So the term is basically the sequence inside of the policy statement. So we'll say that this is term 10. We're giving it a name. And what do we want to do with the term? So we're going to say it is from. We could say it's from a, and we'll let's just say edit that, and then we'll set question mark. So these are all the different things that we can match. So for example, we could say if it comes from a particular protocol, if it came from a particular neighbor, if it has a specific next hop value. Then we start to get into details of things like the BGP attributes. So what's the local preference? What's the origin code? What is the community value? What's the particular AS path information that the update went through? So essentially any of the attributes that you would normally use for BGP policy application, this is where they're going to be matched inside of the specific JunOS syntax. So this is specifically here, we're under edit policy options, the policy statement, which the name is policy 1. The actual entry in the policy statement is term 10, and then we're specifying where it is from. So we could say, for example, set protocol OSPF, and then what are we going to do with it? We're going to, once it is from OSPF, we're going to go up one level, and then we're going to set the then, so what do we do? And we're going to reject it, or we're going to accept it. Okay, the other actions besides just permitting the prefix or denying the prefix, of course, you can set the attributes. So if you want to send me a particular prefix with a community value signaled, I can say if the community is true, then set the local preference to be 1,000 or whatever particular values that we want to apply. Now, one of the things that is also nice about this, so if let's say we set then reject, for example, and let's say top show pipe compare. So these are my uncommitted changes. We have the policy option, policy statement. It says term number 10 is if the route is from protocol OSPF, then we're going to deny it. We're going to reject it. Now, just like in iOS or in iOS XR, these statements then are going to be processed top-down. So this normally means that your most granular matches, we want them to be at the top of the policy. Because if I were to say something like, is it from OSPF? If so, then reject it. Then follow it up with another statement afterwards that says, if it's from OSPF with this particular metric type, so is it an E1 route, is it an E2 route, does it have this particular metric value? Based on the way that the matching logic is working top-down, once there's a match in the policy, then it's going to exit out. So there are certain cases where the order is significant in the policy, but one of the nice things about the JunOS syntax here is that you can use the command insert to move different options around the policy. So for example, in our particular case, I have a term called term 10 that's saying if it's OSPF, I'm going to reject it. But let's say I want to put something above this, where I'll say, I'm going to go up to policy 1, and I'm going to set, let's say, set term, we'll call this term 5. And we'll say term 5 is going to say from the neighbor, for example. Okay, from the neighbor 1, 2, 3, 4. If it is from the neighbor 1, 2, 3, 4, then we're going to accept it. If we top show pipe compare, we can see term 5 is now listed after term 10. So this means that if the route is coming from the neighbor 1, 2, 3, 4 and it was from OSPF, then it's going to get denied because the second statement doesn't get processed if there's a match on the first statement. So once we create the new sequence, or essentially the new term, we can then insert the term and say, I want to move it above this particular value, or I want to move it between these two particular values. And the way that you would do that is to say insert, and the term is term 5. Where do I want to insert it? I want to insert it before term, and then term 10. So this you have to create the term first. So notice that I did the editing first, which was to set the options. Then once it was created, I can use insert to move it around. And if we look at the top show pipe compare, we can see now term 5 is being processed before term 10. So if we commit and quit and show config policy options, we can see that's our policy statement. If we show config policy options, pipe display set, these are the specific syntax terms that we would use in order to create the policy. So you'll see in general that as the policy starts to grow, and this is very typical in internet BGP routing, like if this is my PE router, I probably have some type of complex policy that's either for my global unicast peers or for my L3 VPN peers. So when you're looking at it in the set syntax, sometimes it's hard to decode what you're really doing with the policy. But when you look at it in the normal stanza format, it's a little bit easier to read because you know exactly what the hierarchy of the statements are. So this one is processed first. If it's from the neighbor, then we're going to allow it. If not, then if it is from OSPF, we're going to reject it. Now, once it gets below this and there's no match beyond it, the default option actually depends on where we are applying the policy. So we'll see that when we get to BGP, the default policy application is different than it is in RIP or in OSPF. So in general, and instead of trying to memorize which protocols have which policy applications, you can simply define what do you want the default action to be. So if I want the default action to be permit, then I would say under this particular policy, we'll go to config, edit the policy options, policy statement, policy 1, and we'll say set, then accept. And if we show, notice that after term 5 and after term 10 is processed, then we go down to basically our default action, and the default action now in this case is to permit. So if we were to think of this from regular iOS syntax, this would be something like this, where we would say that we have a route map 10, or a route map, whatever. Route map map1, permit 10 says match source, match IP route source 1, 2, 3, 4. Map 1 deny 20 match source protocol OSPF. Like OSPF 1. Route map, map 1, permit 30. And if we then show run, section route map, this basically would be the equivalent. So we're saying that there's a first statement. Well, actually, the first statement is, let's say show run or show route map. Match IP route source. It may be because the source doesn't actually exist, but the logic is the same in being that it's processed in a top-down fashion. Now, in terms of regular iOS, it's more difficult to edit the route map. Normally, you would have to copy it out, make your changes, remove the old one, and then replace it back in. In the case of iOS XR, there's editors built in to XR itself, like you can use VI or you can use Nano directly to edit the RPL. In the case of JunOS, you can just insert the sequences however you want.